Okay, now we're going to look at one-dimensional motion in a little bit different way. We're going to look at it graphically. So let's say we have position as a function of time. Position we're going to measure in meters. Time we're going to measure in seconds. So this is 1 second, 2 seconds, 3 seconds, etc. And this will be 5 meters, 10 meters, 15 meters, 20 meters. Okay, so initially we'll start out at the origin. And let's say in 2 seconds we traveled the 10 meters. And then let's say we stay there for a few seconds. And then let's say we go another 5 meters. And then let's say we quickly reverse direction. And now let's say we go back to the origin in the next second. And then at a little bit slower speed, then we travel out to -10. And then let's say we stay there for the remainder of the time. Okay? So again, this is position as a function of time. We started out at the origin. We went to 10 meters. We stayed there for a little while, and then we went to 15. Then we quickly went back to the origin, and then we went to -10. So let's see what that would look like if we look at the velocity for that same time period. So velocity we'll measure in meters per second. Time is in seconds. And let's say now for velocity we label 2, 4, 6, 8, and 10. So in this first time period we see that we went 10 meters in 2 seconds. So we had an initial velocity of 5 meters a second, and it's constant for the first 2 seconds because, as we see, it's a straight line, right? And velocity is just the derivative of position, so it's just the slope of this line. Okay. In the next time interval, we see we have 3 seconds where we just stayed at 10 meters. So that means that our speed and our velocity is just 0 for the next 3 seconds. Then we see that we went 5 meters in 1 second again. So in position we've increased, but in terms of velocity, this is just that same speed that we were traveling before, 5 meters per second in 1 second. And now we see we went 15 meters, -15 meters in 1 second. So 2, 4, 6, 8, 10, 12. So it looks like this is actually going to be, off the charts. We're going to be down so far. Let's say that this is 15, just to make sure we can actually see it on the screen. And so then for the next second, we're going at -15 meters per second. Okay, so we had a very sharp change in our velocity. So a very steep acceleration. And then we see that we went 1, 2 seconds. So in 2 seconds we went -10 meters, so -5 meters per second. So 2, 4, 5. And so we traveled at 5 meters per second for the next 2 seconds. And then the position was constant at the end, so our velocity is just 0. So this would be a velocity for this graph. Now, one thing we'll note, remember, is that acceleration is the derivative of velocity. And so right here, at these points, these are the only times that we really have an acceleration in this graph. And the thing to note is, because I drew it in this way, where this isn't very realistic. It's easier to see this way, so I draw them with straight lines. But realistically, these curves would have to be a bit more rounded, because I have to have some acceleration in this period. Because if it's just a straight line like this, it's basically an infinite acceleration. Okay, so more realistically, I could just have a very sharp peak here, and that would just mean like a really sharp acceleration, like just slamming on the brakes, or some other effect where we have like a really sharp, a really quick change in our velocity. Okay. So we can also do this. So we can also do the same thing for velocity now. Although first, let's look at a couple more things in terms of this position graph. So notice that the sign of the velocity doesn't depend on the sign of the position. Okay, when the position, because like if we look at this time interval right here, we see that the position's positive during the whole time interval, but the velocity is negative, right? Because velocity is just the slope of this line, so it's how much this is changing. So even if our position, had been down for a little while and then come straight across, this time period would still have a negative velocity. And the reason it would have a negative velocity is because the slope is negative. Okay, so that's an important thing to note, that positive position doesn't necessarily mean a negative change in velocity, and vice versa. So we'll do that with velocity now, so you can see. So now let's say we start out with an initial velocity like we did here. We'll start out with 5 meters per second. So again, we'll label this 2, 4, 6, 8. And so we'll start out at 5 meters per second, and then we'll go up to 10 in 2 seconds. And let's say we're constant at 10 for another second. Let's say we decrease for 2 seconds down to 6, and then let's say we're constant again. Now let's say we increase back up to 10. We stay there for, we increase up to 10. We stay there for a second, and then we quickly decrease all the way back down to 0. So now we notice that our velocity was never negative during this entire time period, right? So all we've done is add positive velocity to the particle. And so let's see what this would look like in terms of acceleration. Okay, so if we do acceleration as a function of time, in meters per second squared, and again this is time, this is time. Okay, so we start out at 5 meters per second, and we increase to 10. So we increase by 5 meters per second, and we do that in 2 seconds. So 2.5 meters per second. So again, we'll go 2, 4, 6, 8, 10. So we had an increase of 2.5 meters per second. So this is our constant acceleration in this period, the slope of the velocity line. Again, the next second velocity is 0, which means acceleration 0. Okay, now note that we still have a positive velocity, but we're still slowing down. That velocity is slowing down. And it's slowing down by 4 meters per second in 2 seconds. So we have a minus 2 meters a second for the next 2 seconds. So again, here, see that we have a negative acceleration, even though we still have a positive velocity, because the velocity, the change in velocity, is slowing down. Okay, and then we go back to the origin, and then so for 2 seconds, there's no acceleration. And now notice that we increase by 4 meters a second in 1 second. So now we have a sharper increase in our acceleration for the next second. And then we stop moving again for a second. And then we increase by 10 meters a second in 2 seconds. So now we're going at minus 5 meters per second for the rest of the time. And I mislabeled this. This should have been at 2.5, should have been about right here, not there. Okay, so now we see what our acceleration would look like in terms of velocity there. So hopefully this gives you a good idea of how to do these. Your book has some practice problems Halliday, Resnick Walker has some practice problems, and I can guarantee you that on the exam you're going to have a problem where you have to do this very thing. And so, you know, so for example, if you had to look at, the velocity is a function of position, or the other way around, this is how you would do that. Okay. So now in the next video, we're going to look at some more graphs of one-dimensional motion, but now we're going to go the other way, and we're going to look at what happens if we have velocity and we want to find out what the position is.